Okay, so a key part of the syllabus in computer science, probably one of the first topics that comes up or should come up, is how do you recognize, decompose, and then solve a problem or abstract it? So problem recognition, decomposition, and abstraction. So it's worth, like, this article is in the link below, so you need to read all of this. And once you've read all of this, then you go and look at the past paper questions, which are at the end. And I've picked out some past paper questions from a couple of different papers, one from the 2023 paper, where they ask you about problem decomposition and recognition in relation to a specific example. So once you understand what those things mean, then you're able to answer these questions. And I've also put the answers there as well. But you need to do that. So what is a problem recognition and decomposition? Well, first of all, let's just talk about problems. So there are some problems that are tractable and there are some problems that are intractable. So in this example here, the intractable problems are ones where the computational power required to do them, or the number of steps, is exponential. So 2 to the power n. That's where, say, the number of items in, for example, you could talk about this in terms of sort and search algorithms, or and when the number of items in a list becomes of a certain size, the search time becomes like ridiculous. So tractable problems are ones that are solvable, such as polynomial time, n squared, perhaps, linear time, or logarithmic time. So if you've watched any other videos or you know any other algorithms, you know which ones those would apply to. Big O notation. Okay, so what are the features of a solvable problem? Well, a problem that can be solved, you could abstract and decompose the steps of it. So, for example, looking at the London Underground, in 1931, a guy called Harry Beck created a map of London that of the London Underground that wasn't to scale, but it abstracted out all of the features that were not necessary for you as a traveller on the tube to know how to get to A to B, from A to B. Like, you don't really need to know whether there are parks or roads or anything in between, and you don't really need to know even like the actual geographic direction of the line, as long as you kind of have a general line, that the idea that a line is going from north to south or east to west, it doesn't really matter. So you can see here in this example, this is a map of the London Underground to scale and showing the actual curves and lines of the tube. And then this is one where, with Harry Beck's design, where, for example, like the red line, the central line, even though in reality it does go across London, it kind of goes at a slight angle. His one just goes straight across. So either the lines are basically horizontal or vertical. There are some diagonal ones. So he's removed all the features that aren't necessary. So once you've and then how would you go about decomposing this so that you knew which things to include and which things not to include? Well, for example, you could identify core components. So decompose the map into essential elements. So what is essential in this map? Well, we definitely need to know where the stations, the lines, and what the connections are between the stations. So on the London Underground, if you ever travel on it, you'll see that smaller, not that important stations are just little marks on the line, like Knightsbridge here, or Hyde Park Corner. And then stations which have like a lot of connections have a big white circle with a black outline. So you know that you're going to a station that has connections and you can get off and change there. And then they've also marked out key stations such as like train stations. So also you might want to simplify individual elements. So focus on one line at a time and strip away the exact geographical data So it's, as I said before, instead of representing it as a straight line or gently curving line, like on here, you can just have like horizontal or vertical. And also you could standardize the distance and angles of the lines. So he made it so that there's a limited set of angles, such as 45 degrees or 90. So you'll never see a line at like 30 degrees or 20 degrees. Like on this one, it's just like 90 degrees or 45. And so that simplifies it and makes it easier to read and look at. Yeah, so once you've decomposed the steps of a problem, you're then able to abstract out all the things that you need to solve that problem. So that is one example of a feature that makes a problem solvable. The next idea is enumeration. So an example here could be that you're trying to crack the padlock of a padlock that has a 4-digit code. To open it, you could try to systematically use every single combination from 0 to 999. That would be a brute force attack. So you start at 0, 0, and then you go to 0, 1, 0, 2, 0, 3, and stop when the padlock opens. So, I mean, that's still going to take a lot of time, you're not necessarily, you're going to have to work through a lot of different combinations. But that is one way to solve a problem, by enumerating over it many, many times. And when we look at, if you haven't already looked at some of the search and sort algorithms like binary search, you're enumerating over a certain set of steps until you get to a case where you've either found the item that you're looking for or you haven't found it, and then you stop. Also, other ideas of what makes a problem solvable is having a theoretical approach. What do we mean by that? One example here could be simply you're balancing your bank account or a checkbook, and every time you make a transaction, it affects the balance. So you can calculate your current balance and predict future balances of it. So what we're doing here is we're applying a mathematical approach to trying to understand someone's bank account, and that could be a problem that may be solvable to help you save money, for example. And of course, and the last one is that if you can simulate and automate problems, then you're going to be able to solve them, even when they seem very, very complex, such as weather forecasting. So weather forecasting is very, very difficult because there's a lot of different things that come into it: the wind, the rain, the temperature, the geography of where a country is, or whatever. But if you can input enough variables into a computer and it can use that to create a simulation of it, then even though all of those things may seem random and chaotic by chance, you can get some idea of a prediction, you can simulate the weather, and therefore you can come out with a solid conclusion of whether or not it's going to rain or not. It's going to be a hurricane or something like that. So simulation and automation. So these are some of the features of problems that can be solved. If you can simulate and automate them, you can apply theoretical mathematical approaches to them, you can enumerate over them, and you can also decompose and abstract out the problem from it to make it more easy to solve. So whenever you're programming anything, or when I'm programming anything, one of the first things I do is I think about, what am I trying to achieve? I'm trying to make a website that does this, this, and this. Well, what are all the features of it? Well, I might need a login. I might need a page for like to show the items on it. Perhaps I'm making a web shop. I need a cart. Well, what do I need behind that? Well, I need a database, and then so I'm breaking that problem down. I'm thinking about it, and then I can then go, right, well, which one of those may I need to enumerate over? Perhaps I need to enumerate over calculating the value of the items in the basket. So I need to run through each item in the basket and add it up. That's enumeration. And then simulation and automation. perhaps there's a way of recording what people are buying, and you can simulate in future what items they might be interested in. Often when you go onto Amazon, they've applied AI and algorithms like that to try and understand your buying habits. The other part of problem solving is firstly recognizing a problem. So this example here is looking at traffic lights. So you've got an issue where people are getting stuck at traffic lights for a long time. The first thing you need to ask yourself is there a problem that needs to be solved? Is there a problem that needs to be solved? Then what's the nature of this problem? What things do we need to gather about it to figure out what the problem is, to understand it? And then what variables that we could put into it that could alter the current state of the problem? And then finally, what processes and techniques could we do to solve that problem? So, is there a problem here? Well, yeah, there is. There's congestion at the crossroads. Okay, so what's the nature of that problem? Well, the traffic lights may not be timed optimally, causing unnecessary delays, or perhaps the junction is not designed very well. So, well, how are we going to go about working out what the actual issue is? Well, we're going to need to gather some data. So maybe you need to go and stand at the traffic light and monitor the traffic passing through and actually firsthand try and understand the issue. Maybe the timing of the lights is long. Maybe there's a bug in that program. Get feedback from commuters. And then what variables are in play that could alter the current state? So, for example, as I just said, the timing of the lights, the volume of the traffic at different times of day, maybe the presence of pedestrians, maybe there are other intersections nearby that affect it. And then, well, considering all that information that we've gathered, so we've understood that there is a problem and there are certain things that are contributing to it, then we can go away and come up with a solution that could solve it. So maybe we need to consider engineering the traffic in a different way. Perhaps adjusting the timing or having a smart traffic control system, or maybe even redesigning the intersection or building another road to direct people away from that. So the idea of problem solving is that we want to break the problem down from a first principles perspective. So you strip it into its fundamental elements. The flow of traffic and the control mechanism, which is the traffic light system. So basically, you could apply this to a project that you're working on, So say your computer science project, you're trying to come up with a solution for something. Well, you need to go and find a problem somewhere in the world, right? And so you've got to recognize what that problem is. And then we've got to go and gather the information so we understand whether or not there needs to be a solution and what perhaps that solution could be. And then you need to use that research, that analysis, to suggest what the things are that you could do to help with that issue.